So here we have two oxidation reduction reactions that balance a little bit of a special way that require the half reaction method. So once again, this is something that takes quite a bit of repetition and practice, and it's not something you're often going to be asked to do in its entirety on an AP question or exam. But we will practice it in class with labs and make sure that we hit it again in the oxidation reduction section of electrochemistry. So here we have the reaction of the iodide ion reacting with the permanganate ion to make the iodine molecule and manganese dioxide. It also says it occurs up here in acidic solution, and that's important because we know all of these things are aqueous, but that there also has to be hydrogen ions floating around, and we'll see why that's important. But before we get into any of the things in blue here, what we would see is that this reaction is going to be impossible to balance by a, quote, normal way. The left side has negative charges, but the right side doesn't have any. So no matter what coefficients I put over here and over here, I will never have the same charge on both sides. The other thing is I can balance the iodine with a 2 and a 2, and the manganese is pretty close, but there's 4 oxygens here and 2 oxygens there. If I try to change the number in front of the manganese, it throws this off. So I could balance the oxygen, but not the manganese, or the manganese, but not the oxygen. That's why this is a different way. We can't just go based upon the 3 elements that appear. There's going to be more things involved, and we'll see what that means. But the first thing we do is assign oxidation numbers to everything. And a monatomic ion has its charge, so that iodide is truly -1. All of the oxygens in these compounds are going to be -2, so I have 4 -2s for a total of -8. But because permanganate overall is -1, the manganese in permanganate has an oxidation number of +7. Over here, the iodine is 0 because it's diatomic and it's not an ion. The oxygen's still -2 here, but the manganese is +4. So we didn't really apply it on the previous problem, but we can tell what's oxidized and reduced by looking at these changes in numbers. Manganese numbers goes down, or another way of saying something's going down is that it is reduced. So it goes from 7 to 4. Iodine goes from 0 to 1, or -1 to 0. It's going up. So that allows us to know that the iodide is being oxidized, and I'm going to focus just on this side first. It goes from I- to I2. I knew that it was the oxidized because it went up in oxidation number. But right there, it's not balanced. So I first balance out the atoms themselves. Well, now there's 2 I's on this side and 2 I's on that side. But the charges are not balanced. The way I can balance the charges is by accounting for electrons. So if I have 2 iodide ions making an I2 molecule, an iodine molecule, it does that by releasing 2 electrons. So the oxidation that is occurring is when 2 iodides make iodine by oxidation is losing electrons. Over here on the reduction side, I'm focusing on the manganese. Yes, there's oxygen involved, and we do include that because it's a part of the compounds that the manganese is in, but the oxygen isn't changing oxidation number. It's not going up nor down. So when I look at this, I recognize that my manganese, I have 1 here and 1 there, so I don't need any coefficients. So now I need to think about what's true with the oxidation numbers. To go from 7 to 4, it does that by gaining 3. By 3 negatives coming in to make that go down by that much, or reduction is gain, GR. So then I've got that, but now my charge is even further out of whack. I've got negatives on this side and none on that side. It said acidic solution, and this is what's new. This is what we've never done before. This is what you just kind of have to trust the process and know that it's the right thing to do, is that those hydrogen ions that are floating around in solution must be a part of this half reaction to balance out the charge and to just balance out the charge. So since I have -4 on my reactants, I put 4 positive hydrogen ions on my reactants as well. But now I'm even further from my atoms being balanced because not only do I have extra oxygens, I've got some hydrogens that aren't accounted for on this side. And that's where the solution part comes in. Well, I've got 4 hydrogen atoms, I guess, technically ions, and 2 oxygens hidden here in the permanganate that are not balanced out. That's because those hydrogens and those oxygens make water. Although they are not oxidized nor reduced themselves, the charge presented by the hydrogen that then allows the reaction to happen is what lets this reduction happen the way that it does. Sometimes we are only given this part right there, but every now and then we're given the full half reaction already written with any waters and ions. And we'll see that in the electrochemistry. So my 2 half reactions are the iodide ion losing 2 electrons and the permanganate ion needing to gain 3. The problem is this can't gain 3 if this only loses 2. This can't lose 2 if this needs 3. So we have to find the least common denominator. That was one of the last few steps in the explanations. There was multiplying everything in the reaction by a coefficient so that the total number of electrons gained by the reduction, right here, 6, is equal to the total number of electrons lost by my oxidation, right there, 6. And I tripled this one, making that 2 to 6, 1 to 3, and then up to 6. And here I went up to 8 to 2 to 6 to 2 to 4. Now that I have those, I combine those 2 reactions. 6 iodides react with 8 hydrogen ions, and 2 permanganate ions. Those are all of my reactants to make manganese dioxide, 2 of those, 4 waters, and 3 iodines. And the 6 electrons which are gained in the reduction and the 6 electrons which are lost in the oxidation don't need to be in the overall. Very similar process down here. I wouldn't say it's necessarily any easier or harder. We have copper becoming a copper ion and the nitrate polyatomic ion becoming nitrogen dioxide, probably gas. So this also occurs in acidic solution, which means there might be hydrogens or waters involved as well. The copper by itself, the copper in the compound, we know very easily what their oxidation numbers are. The oxygen in compounds, we know very easily. And by process of kind of elimination, just like we did with the manganese, if I add 3 minus 2s for a -6, that means the nitrogen has to be a +5 to give that -1 overall. And if I have 2 -2s for -4, the nitrogen's +4. So, although not the exact same numbers, a very similar process. The copper is what's oxidized as it goes up in number. So whether we're going from negative to 0, negative to positive, 0 to positive, or positive to even higher positive, that is oxidation. We are increasing the oxidation number. So the copper itself is balanced. 2 electrons balance that the rest of the way. So that not only are we showing that we are losing 2 electrons, but the charge is also totally balanced. As nitrate becomes nitrogen dioxide, we are only gaining 1 electron. We're going from 5 to 4. So we put in 1 electron there. So nitrate and an electron makes nitrogen dioxide. But just like before, our charges aren't equal. In both of these cases, hydrogen ions go on the left, but technically hydrogen ions could go on the left or on the right. Hydrogen ions and water molecules could be in the reduction or the oxidation. I just kind of chose 2 that were similar to one another here, somewhat unfortunately, because they kind of look the same. But after I do that, I recognize that I have extra hydrogens and an oxygen on the left, which allows me to know there's a water on the right. And then as I double it, I do that because I see just 1 electron here as opposed to the 2 electrons lost by the copper. So now my 4 hydrogens and my 2 nitrates will react with the 1 copper atom, and that will make 2 nitrogen dioxides, 2 water molecules, and 1 copper 2 plus ion. So as we do this, the keys are oxidation numbers. Then whatever goes up in oxidation number is oxidized, meaning it loses a certain number of electrons. and it loses enough based upon how much the oxidation number increases. Whatever goes down and oxidation number is reduced, it gains a number of electrons equal to however much it went down. From there, we use hydrogen ions and water molecules to balance out the charge, the hydrogen atoms, and the oxygen atoms, based upon the fact that if this iodine, permanganate, iodine, and manganese dioxide are all floating around in water, the hydrogen ions in acidic solution can also participate in the reaction in order to balance out the charge. As we look at our initial to our final reactions, it's very obvious that we'll never get from point A to point B without breaking it apart or having this sort of strategy. There's no hydrogens or waters obvious in the initial reaction. Those get put in. But the good news with this is very rarely do you have to go from this reaction down to there all at once. It's much more common that you are given the half reactions, maybe in their nearly complete state, or that you were just asked about how many electrons are gained or lost, or a coefficient on just one or two things. This is a vital process to practice. It's a very important thing to do your best to understand, but it is not the most important thing to master, no feeling like it's going to be on many tests, quizzes, and the AP exam.